Hi and welcome to Module 9.2 of Digital Signal Processing. We are talking about digital communication systems, and in this module we will talk about how to fulfill the bandwidth constraint. The way we're going to do this is by introducing an operation called upsampling, and we will see how upsampling will allow us to fit the spectrum generated by the transmitter onto the band allowed for by the channel. Remember that our assumption is that the signal generated by the transmitter is a wide sequence, and therefore its Powell spectral density will be full band. What we need to do is to shrink the support of its Powell spectral density so that it fits on the band allowed by the channel. The way we do this is by using multi-rate techniques. In multi-rate, the goal is to increase or decrease the number of samples of a digital signal. One way to do this is to interpolate the digital signal into a continuous time signal and then resample the interpolation at a different sampling rate. However, we want to avoid the transition to discrete time, and we want to perform this artificial change of sampling rate entirely in the digital domain. Let's consider the upsampling operation, which is really what we're interested in. And let's look at how to do this, going through an interpolation and resampling operation first. So we have a discrete time signal here. We interpolate with a given period Ts, we obtain a continuous time signal, and then we sample this continuous time signal with a period that is k times smaller than the original interpolation sample. And we obtain another discrete time sequence here. Graphically, assume this is our discrete time signal, the interpolation to continuous time will give us this, and the resampling with a smaller sampling period will give us a higher density of samples on the same curve, so that the resulting upsampled signal would look like this. Now we are interpolating to continuous time, so the choice of the sampling period is completely arbitrary. For simplicity, as per usual, we choose Ts equal to 1, and here we have that the interpolated signal is given by the standard sinc interpolation formula. When we resample with a period that is 1 over k times smaller than the original, we are taking samples of the interpolated function at n over big K, and the result is an interpolation formula where the sinc function now is centered at fractional intervals, so n over big K. In the frequency domain, the process looks like so. Imagine we have a discrete time signal whose spectrum is limited to 3 pi over 4. We interpolate it to continuous time and we get an analog spectrum that looks like this, where our Nyquist frequency is omega n equal to pi over Ts. When we resample with the sampling period, which is k times smaller, that is equivalent to multiplying the Nyquist frequency by k. So we make it bigger and we move it over here. And when we plot the resulting digital spectrum, we map, as per usual, the Nyquist frequency to pi, which corresponds to a contraction of the frequency spectrum by a factor of k. If here we choose k, which is equal to 3, we get that what was the highest frequency of the spectrum, 3 pi over 4, now becomes pi over 4. Can we do this completely in the digital domain? Well, the idea is that we need to increase the number of samples by a factor k, and obviously the samples in the upsampled sequence will have to coincide with the original values when the index of the upsampled sequence is a multiple of k. There are several reasons why this is so, but probably the most intuitive one is that if we then discard the extra samples, we should be able to obtain the original sequence again. So for lack of a better strategy, we can start by building a sequence where we put the original samples every k samples, and then we put zeros everywhere else in between. So for example, for k equal to 3, the upsample sequence, say this is m equal to 0, will be equal to x0 in m equal to 0, then we put 2 zeros, then we put x1, then we put 2 0, then we put x2, and then we put 2 zeros. We can see this in the time domain. We start with the same sequence that we showed before, and what we are doing, we're simply introducing zeros between each sample. With this choice, the Fourier transform of the upsampled sequence is rather easy to compute. We just write out the standard DTFT formula, but now here we remember that xu of m will be equal to 0 every time that m is not a multiple of k. And so with this, we can simplify the sum, and use only the non-zero terms, and we get the sum from n that goes from minus infinity to plus infinity of x of n, which is our original sequence, that multiplies e to the minus j omega n k. And so this is simply a scaling of the frequency axis by a factor of k. Graphically, we can plot the digital spectrum, and we know that now, since we're multiplying the frequency axis by a factor of k, there will be a shrinkage of the frequency axis like this. But we should never forget that the digital spectrum is 2 pi periodic. So let's plot this explicitly from minus 5 pi to 5 pi. If we choose k equal to 3, we're mapping the interval from minus 3 pi to 3 pi back onto the minus pi pi interval. And when we do that, we get something that is very close to what we obtain going through the analog domain, in the sense that this frequency here is, again, pi over 4. But we have extra copies that have crept in the main frequency interval. Now, we know what to do in these cases. We apply some drastic low-pass filter to get rid of them. We choose an ideal low-pass filter with cutoff frequency pi over k, because this is where the original pi in the frequency spectrum would be mapped to. And this will get rid of the extra copies and leave us with a spectrum that is identical to what we obtain using an interpolator followed by a sampler. So now let's look at the procedure back in the time domain. So the first step is to insert k minus 1 zeros after each sample, followed by an ideal low-pass filter. And we choose the cutoff frequency for the filter to be pi over k, as we saw in the previous graph. So now the resulting sequence is simply the convolution of the upsampled sequence with zeros. And the impulse response of the filter, that with this cutoff frequency will be simply sinc of n over k. And if we work out the convolution sum, we have this summation here. But again, we remember that of these terms, only one every k will be non-zero. So we replace I with mk and we sum over m. And we get the sum for m that goes to minus infinity to plus infinity of x of m sinc of n over k minus m, which is exactly the same formula we got using an interpolator and a sampler. As we mentioned before, if we have an upsampled sequence, we can always recover the original sequence by downsampling, which means we keep only one sample out of k and throw away the rest. Now, this is obvious in the case of an upsampled sequence where we just introduce k minus 1 zeros every sample, but it is also true for a filtered sequence where we use an ideal filter, or any other filter that fulfills the interpolation properties that we have seen in Module 6. In other words, we want the impulse response to be equal to 1 for n equal to 0, and to be equal to 0 for all multiples of k. In general, downsampling is a more complex operation than upsampling, just like sampling is more complicated than interpolation. We have the pesky problem of aliasing because we are throwing away information. We will not develop the properties of the downsampling operator in detail because we will not need it in the following, but you're encouraged to read about multi-rate signal processing in the book. So let's go back to the bandwidth constraint. As you remember, the channel imposes that we only use frequencies between Fmin and Fmax. We also want to translate these requirements into the digital domain. So we choose a sampling frequency, and Fs over 2, half of our sampling frequency, will be our Nyquist frequency in the analog domain. Now, here's the neat trick. Compute the positive bandwidth, namely the width of the channel bandwidth on the positive axis, and call that W. Now, pick the sampling frequency so that two things happen. First of all, the sampling frequency will have to be at least twice the maximum frequency that we can use in the channel to avoid aliasing. But then we choose the sampling frequency as an integer multiple of the positive bandwidth. So we say that Fs is equal to kW for k a positive integer. With this choice, when we translate the analog specifications into the digital domain, and remember the formula is always the same, 2 pi f over Fs, what happens is that the bandwidth in the digital domain will be 2 pi w divided by Fs, which is equal to 2 pi over k. And so we can simply upsample the symbol sequence by k so that its bandwidth will move from 2 pi to 2 pi over k, and therefore its width will fit on the band allowed for by the channel. Now, upsampling does not change the data rate, because we're creating a sequence of symbols from the user data bit stream, and then we're introducing zeros between samples, so we're not introducing extra information. So we produce and transmit W symbols per second, and then we upsample that by K to achieve a sample rate which is equal to the sampling frequency. W, therefore, is the fundamental data rate of the system, and sometimes it's called the baud rate of the system. A golden rule for digital communication systems is that the baud rate will be equal to the positive bandwidth allowed by the channel. So here is our revised block diagram for the transmitter. User data comes in as a bit stream. Scrambler makes sure that we have a random sequence of symbols. The mapper will create the random sequence of symbols. We upsample this sequence by K. We filter this with a low-pass filter with cutoff frequency pi over K, and we obtain a baseband signal B of n, which is centered in 0 and extends from minus pi over K to pi over K. Now we need to move this baseband signal to the passband of the channel. And to do so, we modulate it with a cosine carrier whose frequency is the centered frequency of the channel's band. This passband signal S of n can now be converted to the analog domain before being transmitted over the channel. Graphically, assume these are the specifications dictated by the channel and translated to the digital domain. So here we have the positive bandwidth and the negative bandwidth. The sequence of symbols generated by the mapper is a wide sequence, and therefore its power spectral density, Pa of e to the j omega, is a full band signal. Now when we upsample this sequence by a factor of k, we reduce its spectral support to a baseband signal that goes from minus pi over k to pi over k. And then we modulate this with a cosine carrier to fit it onto the bands that are available on the channel. As a final note, since we are developing a completely digital transmission system, we will probably want to use FIR filters in its implementation. Now we know that the sync filter that we have used in the upsampling operator will be a notoriously difficult filter to approximate with an FIR. So what is used in practice is another type of filter called the raised cosine. The frequency response of the raised cosine is shown here in this picture, and you can see that the transition band is no longer a discontinuity, but it is actually a smooth transition from passband to stopband. As a matter of fact, the raised cosine has a parameter that you can tune to have an even gentler transition band. Now, the raised cosine remains an ideal filter because you can see it is constant over the passband and the stopband. But it is much easier to approximate than a sync. Another good property of the raised cosine is that it fulfills the interpolation property that we need to do upsampling. And the final selling point is that the impulse response, it can be shown, decays as 1 over n cubed. So even short FIR approximations can get a very good response.